Sorry?
All the access must be reasonable, yes.
Ah.
Really?
I think Samson was going to rest. Is the cameraman ready to go? Okay, well, welcome to the afternoon session of the second day of the Canton Theatre. So we have two talks, and there'll be a double whammy. I think they form a sequence, right? The first one will be a talk by a mathematician employed by a computer science department telling us about physics. The second one will be by a physicist employed by a computer science department telling us about mathematics.
Something missing.
Very nervous. Okay, so what I really want to tell you some of the trade secrets of topos theory that you wouldn't get just by looking at the big calculations that are done when the topos approach is explained, and this is something that, I mean, what makes these tricks work are kind of subtle, well, it's logical tricks basically. If you restrict the logic enough, things work nicer, but it's not clear whether it's valid in any given situation. But you can restrict the logic enough. Is your mathematics going to respect the constraints? So what I want to do is outline what the program is, what we're trying to do, and there seems good evidence that we should be able to make it work within these constraints. But it always is hard work and you've got to knowledge things that we do stuff. So I want to tell you what we're trying to do. So when people see the topos approach, the first thing they think is, why topos? What's it actually buying you? You've got some world there where you've got non-standard truth values, but why topos is, and would any non-standard truth values do? And what I want to do is give a justification that is in terms of bundles. Right? So why topos is meant to be, this is meant to be the answer to why topos is. And along the line I'll explain to you what are the logical tricks that make this work. But actually there's something else that happens, which is, by the time you're thinking in terms of the bundles, you can leave aside some of the detailed internal calculations that you get inside the toposes. So it's meant also not only to explain why toposes, but also to make it easier. So as I say, it doesn't apply to all topos theory, but there's a big substantial fragment that does apply to topos theory, and this is the fragment where I feel the most comfortable working. And it helps you avoid the big calculations. So first thing, what is a bundle? So I'm going to give a technical definition of bundle, which is any map, except when I say map, I always understand continuous, from some space to another. Okay? Now, why on earth, we've already got a word to describe these, which is map, so why on earth call them bundles? And the reason for this is the conceptual idea of bundles. So this is family of spaces yx indexed by x as a point of place space. So each yx, this is going to be the fibre, the inverse of x, which I may also write in some places x star of y. Right?
You don't even want P to be a certain.
Nothing, no. In fact, in some cases it won't be a no. And this is a reasonable level of generality, as you'll see when we get to the big theorem in the middle that lets it to the topos. But I don't. Obviously, the standard example is the tangent bundle. So you've got some manifold, and then each point in the manifold, you want the tangent space, and for the bundle, you put them all together, you've got suitable topology that glues the fibres together, and you can make that into a map from the tangent space, from the tangent bundle space down to the base space. But I'm not assuming any kind of manifold structure or anything like this. Any map. Here's a big dream. So the dream is to study bundles by doing topology, but this is quotes, but doing topology with base point x's, right? X's sprinkled everywhere. Okay, so you're talking about a bundle. You say basically you've got a space yx and then you've got this parameter x put in, and so the whole discussion is meant to be parameterized by x. So however you think you're doing topology, you're going to end up with these little x's sprinkled everywhere. So this is a kind of, let's call it dependent space theory. Alright, so you can see, if it's going to work, you can see it's got some kind of analogy of dependent type theory, which is, that's what happens with dependent type theory. Okay, so what's going to make this work in the end is a particular connection with topos. We'll find actually this is going to be doing topology in the topos of sheaves over the base space. And that internal topology is going to be the kind of doing topology with x's sprinkled everywhere. But now there's a big limitation there, because it's absolutely plain that this doing topology, whatever constructions you use on topological spaces, they're going to have to work fibre-wise. They're going to have to work fibre by fibre, because otherwise, you find that what happens in yx is going to be influenced by things happening on neighbouring fibres or in completely different places. So this is a huge clue as to the kind of things that are going to, which is going to be possible to make this work, and what its limitations are going to be. So it must be a fibre-wise mathematics. So the constructions we're going to be interested in. There's actually a good, I'm not going to characterise the fibre-wise operation of the constructions exactly. What I'm going to do is give a slight generalisation, which is the things that we really want. So just to motivate this, if we have the way we can get fibres is by pullback. Okay, so if you've got, here's your bundle, if you've got a point, x, then that gives a map from 1 to x. The fibre is just the pullback of, x star of y. Right, that's why I use that notation up there for the fibre. So, a good generalisation of this is, well, what am I saying? So you want constructions on bundles when you pull them back, and basically the same constructions on fibres. What I'm going to say, the really nice thing, is when it works for arbitrary pullbacks. So this gives us the notion of geometricity, which is going to be so important. So a construction is geometric if preserved by right? So whatever your construction is, you've got some construction on bundles. I mean, we'll see this working with evaluation spaces and various nice things. Whatever you do with your bundle, the same construction, the answer that you get should be well, what am I trying to say? If y is the answer is the result of some construction, then the pullback should be the result of the same construction pulled back to the effect. So this is the notion of geometricity. So we'll be interested in constructions you can do on bundles that are preserved under pullback. Okay. So an example. Yeah, here's an example. So if you've got so an example is products. So if you've got a space X and you've got two bundles over it, then the product bundle, you want to do everything likewise, it is actually just the pullback. So you've got Y1 yes, so this is always going to be preserved by pullbacks along some X. So you find what's your F1, sorry, F star of Y1 and F star of Y2. And up here you've got F star of Y1 plus Y. Product over X. That is isomorphic to the pullback piece. Right. So this that's actually a fairly simple theorem of category, and that's going to be very general. But we'll see other constructions also for which the geometricity preservation under pullback is less trivial. It's going to be a more important factor. So, all right. So what was the dream? The dream was study bundles by doing topology, but with these X sprinkled over. So this kind of presupposes doing topology. You know, we know when you're doing mathematics, you start off with an idea of sets, and then you start defining things in terms of the sets. So it's an important step here is going to be to analyse what is the right notion of set for fibers. So set for a space means it's got discrete topology. Well, that's not making any deep statement. That's just a definition of the discrete topology. But there's an analogous notion for bundles, which is that of local homeomorphism. So local homeomorphism is the analog for bundles of discrete space. So here's a definition. So a bundle P from Y to X is local homeomorphism. If following two properties. So first of all, P is open, and secondly, the diagonal from Y to pullback is also open. Now that's not the definition of local homeomorphism you'll usually see. As far as I know, this goes back to one Joan Tierney paper later. But if you think of what it means in the case when X is 1, and look at what it means for this diagonal map from Y to Y plus Y to be an open tap, in other words, the diagonal subspace is open in the square, you'll see fairly quickly that that's that's a way of characterising discreteness of space. It enables you to prove that all the singletons are open, which is what you want. So this is the definition of local homeomorphism, and that is that's the bundle notion of discreteness. So so there's a category of these things. So a category of local homeomorphisms over X is I'll write it. I'll write it. She's a X. Right? And this is, as is well known, this is equivalent to the category of sheaves when sheaves are defined using the asymmetry definition. So they're equivalent to each other. And that's the topos.
So we need etol bundles.
Yeah. Yeah. Okay. So now, in this topos, I mean, you know that the definition of the topos has got loads of internal structure. So it's got products and co-products and function spaces, and also the suboptic classifier and the power set construction. Amongst those, we should ask, what are the ones that are geometric? What are the ones that are preserved by pullback? Oh, and I should note, if you've got a local homeomorphism and you pull it back, it's still a local homeomorphism. So that will give you a functor that's the inverse image functor from one topos to another. Okay, so which of these constructions? Yeah, so I write down constructions in sheaves over X. I mean, you already know you haven't got all the classical things, but you have got co-limits, finite limits, you've got natural numbers object, and from that, by paper of Johnson and Wraith, you've got free algebra instructions. You've got exponentials, and you've got subobject classifier, and you've got the power object functor. So it's worth asking which of these are geometric, because we know that geometricity is going to be a limitation to whether we're going to achieve our dream. So which of the geometric ones? These are the co-limits and finite limits. These things, the natural numbers object, the free algebras, they're all preserved under these pullbacks of local homeomorphisms. And then when we get to these, so these are the exponentials, there's the subobject classifier, there's the power object, they're not. So this is giving us a dividing line between, at least as far as the discrete functors, the local homeomorphisms are concerned, it's going to give us a dividing line between which things are going to work fibre-wise and which things aren't. So the problem with these ones is that when you calculate these in terms of bundles, you find what happens on a particular fibre is influenced by what's happening on the neighbouring fibres as well. This is the infection of germs, to use the technical term. You get germs of things instead of just straightforward constructions. So this is the geometric fragment of the topos mathematics, and this is what we're actually going to be interested in. Okay, so
Sure, you don't want to abandon exponential power of the two.
we're going to have to if we want to be geometric, and I'll get on to what are the benefits of being geometric. I mean, it's not just to prove our moral superiority to the people who use the non-geometric stuff, but it actually, I mean, basically it's this dream. Once you do it this way, it makes it easier to treat the bundles in a kind of more naturally topological way. Okay, so now there's a very, once we've got as far as this, there's a very key theorem which really underlies the whole approach, and which I can start with. hesitant to rub out the dream, but perhaps I should just do it. So here's the bundle field. So this is absolutely central. And this goes back to, I think it's informing Scott. Certainly in while between. So there's an equivalence between bundles over X and internal spaces in the topos of sheets over X. So this, what this is really telling us is that this idea, well, it hasn't quite told us this yet, but it tells us do topology in there, and we will get theory of bundles. So there are some provisos. So, well, big proviso, space here means point free topological. Space. Alright, so at this point, you may be thinking the thing is turning south, because you might be thinking, well, that's a bit tricky, isn't it? But let's see how this is going to go. So there's actually a nice feature of the geometric reason that has very good implications when it comes to dealing with the point-free spaces. So I'm going to define a point-free space. Point-free space. Well, actually, let me be bold. I'll just call these spaces now. So the space is of the form. The space is given by a propositional geometric theory. So, and I'll write the space with square brackets like that. So what this means, so that you can, so you know what these things are talking about. You have a signature. Well, that's just a set. It's just a set of propositional symbols. And then axioms are of the form phi entails psi, where phi and psi are both geometric formulae built from sigma using finite conjunctions, sounds true in the binding conjunction, or also arbitrary disjunctions.
So when you say propositional, I mean, do you mean that you have a relational signature and you're considering atomic formulas, or just propositional letters?
Just propositional letters. There are no
The signature is, I mean, you just mean a set of you mean a sorted set?
There are no sorts.
No sort.
No sorts.
So it's just a set of letters?
Yes, that's right.
Propositional
Yeah.
letters?
Yeah. I'm using the language which is kind of inherited from the predicate formulation. Okay, so I say this is describing a space. So how does this work? So given our theory here, the points of this point-free space are the models of the theory, and the opens are the formulae. So these are the formulae built in this way using the finite conjunctions and the arbitrary disjunctions. So you can see actually, I hope, that these, what we're doing is we're taking the elements of those as sub-basic domains, and then these correspond to the finite intersections and arbitrary unions that we get in topology. Okay, so that's there's a canonical way of describing these, and this there's a canonical way of describing these, and that's using the frame, which is basically the Lindenbaum algebra for the theory. So canonical description use the frame of opens, which I write like this. So this is lattice of formulae modulo equivalence. So it's logical equivalence in this geometric logic. So that's, you might think that's brilliant, and that's the way to go. We use these all the time. Actually, we'll see why there's a disadvantage of using frames, and there are good reasons for sticking with the theory. So this is something that was certainly discovered also by the predictive type theorists, and they kind of refuse to use the frames and always use things that are presented in the theories. Anyway, so let me stay with that for a couple of seconds, because I'm going to use that to define maps. So a map from one of these things to another is a frame homomorphism. So frame homomorphisms preserve the finite meets and the arbitrary joins, going in the opposite direction. Okay, and also let me say, because I've been talking about the internal mathematics of topologies as well, there's a perfectly good theory of frames in topologies. So it uses these non-geometric things, uses the power object principle. So internally in a topos, frame is, did I say that? Yeah, frame. A frame is meet semilattice. With joins, arbitrary joins, given by a function, power set of A to A, plus a certain distributivity. Okay? So, those of you who've done it, really rolled up your sleeves and done the topos approach seriously in toposes, have calculated a number of these frames and invariably discovered it's a tricky thing to do. So you'll be pleased when I say that it's generally not necessary, and you can avoid doing it. Now, anyway, so that was the canonical definition of the canonical description of the geometric theories. But there are also lots and lots of non-canonical things which are really just presenting the theories. So, for instance, you've got non-canonical. One example, which is very general, is what I call the GRD system. So, GRD system has three sets, GR and D, and it has a triangle, not commutative, but a triangle that looks like this. So G is generations. So that's actually the sigma. R is relations. So that's axioms. is the disjuncts in formula. So that's really just a very succinct way of describing one of these things. And you see, the way you get a geometric theory out of this diagram is you say for each R, you have for each R an axiom which is the meat of lambda R entails disjunction over the fibre of pi at R of the conjunction of rho of this. Okay, so that's I'm not really expecting you to see how general this is, but the fact is this is a succinct way of describing geometric formula. And what this means is that you can see how this is going to work internally in a topos. So you have object. This finite power set, sorry, I should have said that, this finite power set is also something that can be constructed in a topos. Okay, so those are the GRD systems. Now, let me look at the geometricity, because something very strange happens. And it's really about the frames not quite behaving themselves. So if you've got two so suppose you've got some x, and over it you've got some local homeomorphisms. So you've got D, R, and G, and then you've got the F and G. Triangle like this, these are all local homeomorphisms over X. So using the internal stuff in the topos, from that you can present a frame for this thing. Again, it's going to be an object in the topos, it's got the right internal structure to be a frame, so I'll write that as omega GRD. Right. This again is a local homeomorphism. Let me do. I'm going to. Suppose I do orange for the local homeomorphisms, and then the Johannes-Joni theorem, the bundle theorem over there, says that that corresponds to a bundle which is not necessarily a which you might like that. Okay. So all the orange stuff is what you see internally in the mathematics of topos, is just using the objects of the toposes. But it's really describing the internal locale in the topos, and that gives you a bundle over the topos, and that's this bit. Right? They're all bundles, but the local homeomorphisms you think of as objects of the topos as well. Okay, so what happens when you pull that back? So here's something. Here's an exponent. To save a load of writing, let's draw some bubbles. So this is F star of GRD. We've just taken that triangle and pulled it back. So we've got three local homeomorphisms going down there. We've also got F star of this thing. And we've got F star of this thing. So this one is again. Now the problem is, this is not a frame. The frame structure is not preserved under pullback. Actually it's surprising. It's preserved by direct images and geometric models, but it's not preserved under pullback. So that's not the frame. So if we look at what the frame is generated by this thing, in general, it's not going to be that. Let's construct it. So this presents this over here. Another homeomorphism over here. This presents something. So it's going to be another bundle, but actually it turns out to be isomorphic to this one. So what's happened? We've got a triangular relation between three things: the presentation, the frame, and the bundle that we get. You pull it back. Two of those links have been broken because the middle part, pull it back, is not going to be the frame presented. The frame presented is this thing. So you've still got a triangular relation between these two things. But that's not what you got by pulling back. That would have to be between these things. But it turns out the third link, the third leg of that link, the relationship between the presentation and the bundle, is preserved. So when you go the right way around, over this at the top box, from here to the presentation of the bundle, you get the same answer as if you pull back that. So that relationship between the presentation and the bundle is geometric, even though the frame in the middle is not. So that's, well, I proved that in the course of writing my paper on parallel columns, not parallel column exponentiation. So what that says is the geometricity, it's best not to go via a frame. It's best just to think as much as possible in terms of presentations, and then that will be robustly geometric. That's the thing that's actually going to be preserved when you go from one place to another. Okay, so with that in mind, let me now say something about how what are the benefits of geometricity? Why do we bother to restrict ourselves in this way? And essentially, what the geometricity does is it restores the points to the point 3 to 4. It enables us to talk about the points of it. So the way this works technically is that geometricity means preservation under pullback. So if we've got a geometric argument, geometric construction, and we do it on points, it's also going to work for generalized points. So geometric construction of points such as, this is not necessarily going to be the base space, it might be some y. Points that maps 1 to y also work for generalized points. And these are just arbitrary maps. Arbitrary maps from any domain into the y. And so I'll show you, I'll illustrate how this works in practice. Well, the problem with points is that if you just stay in the set theory where you think you are, there might not be enough. And it's an essential feature of geometric logic that it doesn't have a completeness result. And that can give you a shortage of models. And you can get some badly shorted models. But once you start looking at these generalized points, then you've got plenty of them. And that kind of gives you enough points to be able to use points in the way you like to use them. So let me say roughly how you'd like to be able to use points. So here's some typical arguments. You say let x be a point of, remember x here is our base space. So having said that, I mean this declaration has scope, doesn't it? So once we said there's some part of the argument where we're still dealing with x. Once we've declared this x, we're now working in sheaves over x. In effect, inside this box, we're in the internal logic of that topos of sheaves. So from this point, we get truth values. Remember, x is I'm sorry, what I meant was point of some geometric theory. We're now working in sheaves over that geometric theory. So we've now got truth values of the form x. Well, let me write it this way: x satisfies a, where a is in the signature. And this is because, well, appoints a model of that. What does a model of that do? It assigns a truth value to every element of the signature. So we just get model of truth values like this. And then we've got corresponding subsets of one, subsingletons. Right? A truth value gives you a subset of one. It contains the unique element if the truth value is true and otherwise not. So these are in the topos internal setting. These are going to be sub-sheaves of one. Okay, so now let's suppose geometrically, roll up our sleeves up. Geometrically, we do something. Let's construct. Well, what might we want to do? Suppose we're trying to define. Oh, this is a one. Suppose we're trying to define a map from this space to another one. Well, what we'd like to do is say let x be a point, and then you'll define the result of the map as the model of the other one. So from this, geometrically we construct model of T2. Right, that's one thing we might want to do. So once we've done this, what have we got? Well, it turns out what we've got is a map from this point 3 topological space, the T1, to point 3 topological space, T2. So the reason you might think that can't be enough, just to say let x be a point at the first and define the result in the second. But it's okay, because what we're really working with is the generic x in that topos of sheaves, and that as a generalized point is the identity map. And what we do for the generic point by geometricity will work for any point whatsoever, any generalized point whatsoever, including all the actual global points in our own, wherever we think our home set theory is. So it turns out this is quite sufficient to define a map. So we don't have to think of frame homomorphisms from one frame to another. We can just say that x be a point in the domain, define a result in the codomain. Here's another thing we might do. Suppose going backtracking, so we're saying that x be a point, we geometrically construct something. Well, suppose we construct a set. Okay, so geometrically now means using those constructions that I listed. So the topos of sheaves is closed under those constructions, so we've certainly still got another sheaf. So what we've ended up constructing here is a sheaf. So what this is telling us really is that as long as we work geometrically, then you can think of sheaf as a continuous set valued map. So start with a point, for each point you construct its phi map, store that local homomorphism, and that's what you need to do to construct a sheaf. So sheaf equals continuous set valued map. Okay, what else? Right, we said let x be a point, we're wondering what we can do with it. Suppose geometrically we construct a presentation of space. So, e.g., one of these GRD things. Right? I have to say, I mean, these tend to be not the ones that are useful in practice. You construct a POSEC to make an ideal completion. Construct metric space to make a metric completion. suppose we construct a presentation like this, one of these GRD things. What we've actually managed to do is construct, you see, we know we've constructed these now as sheaves, and we know by the the bundle theorem that that gives us a bundle. So we have this. So we've now constructed a bundle over T1. So this is our dream. This is our dream come true. The way we wanted to construct bundles was to just say let X be a point and describe the phi. And as long as you do it geometrically, that's fine. We've done it. Okay, so that's, I mean, that, if you're not careful, or, you know, if you've only just, look, when I first started out, I just ended up writing presentations, but actually you discover that there are space constructions that are geometric in this sense. And what that means is they can be reduced to constructions on presentations like this. Or that's how you prove them. I mean, what it actually means is just the original diagram. It's preserved by Bulber. So some particularly important geometric bundle constructions are, well, the first kind, which is which kind of, I mean, I was saying this is doing topology inside the topos with parameters sprinkled everywhere. But the first kind actually seems like a slightly abstruse kind of topology. But is really quite useful once you get used to it. So geometric bundle constructions. First kind is hyperspaces. Alright, that's not the way topologists usually do topology, but it turns out quite useful in it. And these technically are the power locales, but a lot of the intuition of this, a lot of the usefulness of these, as Samson taught me all those years ago, is from power domains. So the power domains can be put into these geometries. And that gives you some quite cute approaches to doing topology in terms of these hyperspaces are geometric. Another one, very relevant to the topos, to the bottom situation, is valuation spaces. So Vx is a space whose points are, I mean, these are probability distributions, points of valuations on a frame. And I said frame there, but you can prove that it can all be reduced to the to the presentation. So you get a geometric compound. So valuation is a map from the frame to the upper reals. Scott continuous. Mu empty equals 0. Mu of the whole thing. Also mu x equals 1, and we've got the modular law, which relates the values on unions and intersections to mu of mu join plus mu of mu with mu plus mu. So this is, I've written a paper on these things, but this particular manifestation here, that gives the probability distributions. Jerry Capon and Bastitis wrote that up, and it was used in an essential way in the nine-making approach on nine-making paper on topos. So, okay, so I think, how much longer have I got? 7 minutes. Oh, okay. start saying more that may intrude into Beckery's talk. I think I'll just finish off by giving a couple of examples that relate to things people have been saying over the past couple of days. So one example was Andreas's talk yesterday. And I just want to say, what I'm trying to get over here is how, if you view these things as bundles, it becomes quite a bit more clear what's the internal calculation in the topos is actually trying to do. So first of all, here's Andreas's thing. So he is talking about probability distributions or measures. It's not important exactly what kind it was, but he had a map from, well, in his case it was from the measurable subset, so the fx is the set to the frame of a certain I, where I is well, it actually is 0 to 1, including 0. That's over it, that's right, 0. And it had the co-Scott topology, right, which I write by putting an arrow up there to show the specialization order goes in that direction. 0 is top and 1 is bottom in the specialization order. And then its frame is, it's got an extra point in, it's got both endpoints in, and when you think of it the natural way, it's using the Scott topology. So the specialization order goes in the numerical order. Now, this omega I, that has a, when you put the Scott topology on it, you can also see it as the exponential in the category of point-free spaces. These points are maps from I to Sierpinski. Right? Opens of any space are just maps from I to Sierpinski. Sierpinski's got 2 points, top and bottom, and or constructively it may have points in between. Don't worry about that. So where Andreas had this frame, we could write that as a space. It's Sierpinski to the power of I. We think we continuous maps from I to Sierpinski. All right, the exponential property. This is in the category of locales. That's discrete paths. Sorry, spaces. That's discrete paths, but let's just treat that as a discrete space. So you've got sub x cross I mapping to Sierpinski. That's just using the ordinary property of the exponential. You know, it exists there, it lies in the path. Okay, we can, having got this map, we can also pair that with the projection. So we've now got sub x cross I mapped to dollar cross I as a bundle map over I. So Andreas was doing calculations in the topos of sheaves over I. So the things he was working with were the internal objects that corresponded to these things. Now, this one, that, because sub x is discrete, that's a local homomorphism. That's the orange just to prove it. That one's not, but you can factor it through its object point, which is points dollar cross I. So that is a local homomorphism. And this is the discrete co-reflection exactly. So any map from a discrete one to there factors through the discretization. So what I claim Andreas was calculating was these objects and this map internally in the topos of sheaves over that. Okay, let me give another example. So I suppose I'll finish off with this one. So suppose, shall I have some more stuff on? Yeah. this is Hui this morning. So over X, suppose the base space is ideal completion of some P. I mean, that's just a fancy way of saying that we're working out a completion of topics. So what's the internal interval domain? So Samson is suggesting, well, why not look at the capital and see what we've got. So here's how you can actually calculate it. So the internal locality interval domain is this. It's x cross x cross the usual that's I r with the first projection down to x. So Hui was interested in calculating, this isn't a local homeomorphism, so Hui was interested in calculating what the object is down there, which is its set of points of that space. So we've got the point of x cross I r. Now this, taking a set of points, that's not a geometric thing. So it's of limited use. It's not ready to be transported everywhere else, but you may want to do it in particular cases. So how would you calculate this set of points? Well, of course, I said that's going to appreciate topos. So you want to calculate what is its value at each element of P. So what is, if I give this a name, let's call it y. So what is y v for v in P? Well, of course we use Unada's lemma. So Unada's lemma says it's equivalent, it's isomorphic to she's over x or Unada of v to y. So this is an object of the topos. So what does it correspond to as a bundle? Well, it's just up arrow b as an open of that ideal completion. So it's one of the basic Scott opens for that domain. What we're looking at is the bundle morphisms from this thing to R1. So we want to know what is set of these things. Okay. Now that's a local homomorphism. It's just an open inclusion. So there certainly are a local homomorphism. So these things, by what I said about this set of points, they are equivalent to maps from here to that space over x. So I fill in the orange stuff here. That's orange. That's orange. Right. So if we want to know what are the bundle maps from here to there over x, well, we know what the first component has to be because there's a commutative triangle that tells us. So all we really want to know is what are the maps from up to the interval domain as a domain. So that's the continuous maps from up to the external interval domain. So that's how you do the calculation. For the one that's absence fixed, for the locality. So, you know, that's not to say that's the one you're actually working with. In fact, you can various uses. That's how you calculate the locality. So, I suppose I'll stop there.
So a global element would be the map from the whole of P, continuous map from the whole of P to IR.
Well, a global element would be, yes, so that's right. So it's a continuous map from the idea of completion to I bar. And yes, you're right, it's just enough, those are arbitrary ideas, it's just enough to look at the principal ideas, so it's just a monotone function from O of P to I bar.
It's quite interesting. This would be larger complex or assigned things which are larger in the interval domain sense are smaller intervals, which is exactly what we want. I just wonder because we mostly this looks like a covariant situation.
Yes, so your
Yeah.
P would actually be off.
Yeah, that's a weird thing. It's exactly what Paul said. We arrived at the same conclusion somewhat differently. This is what you would get in the liming, the covariant picture.
Yeah.
They argue they want it the other way around. Actually, they want.
Well, somebody's confused. Maybe all of us.
And we want it this way, but we also get the other way around. So both of us get the way we don't want actually. Still, it's very interesting to see the same conclusion we want. But this should be the internal interval. Then we have something which is closely related, but not quite the internal interval. It's maybe the Lawson dual, as you said, or something.
Actually, I mean, thinking about it, I don't think the Lawson dual is going to be quite right. It would somehow miss out the maximum.
Oh, right, okay. Well,
I think. I mean, I haven't
yeah,
said,
so I think
tried it out on paper and pen.
I have one more question. Is there any chance you do this to simplify the calculation of the internal Gelfand spectrum, at least the external description of the internal Gelfand spectrum? Because that has been a lot of work for the Dutch group, understanding how does this guy look externally, and they use quite massively Jimmy internal Gelfand.
Well, okay. I mean, that's something we've been thinking about very hard.
Yeah.
It's something we wrote down explicitly in the project proposal. So they're using the results of Bellairs and Mulvey, so that that paper proves the Gelfand duality in a topos. And there's something that's not quite geometric about it because their C-star algorithm, which has to be completed, will still tend to be an object in the topos. And the description of completeness is something that's not geometric. So what we've been working on is trying to get I mean, we haven't succeeded yet, but we've got a lot of calculations done, is to get an account where the C-star algebra itself is also not necessarily discrete. It's not necessarily a local homeomorphism, which is what you'd expect because it's, I mean, it should be, if X is the spectrum, which is compact, it's completely regular, then the C-star algebra should be that it's a complex vector space, so it should have its own topology. You'd expect it to be the locale exponential of C to the power X. And so what we're trying to do is work with the C-star algebra as incomplete, and from which we then get the completion. So that one would be discrete objects of the topos, and get the completion is the true C-star algebra. So the Dutch have done calculations. I mean, I think they've recognised this, but they've done calculations that show you can get around it in many ways.
Okay, thanks again.